Welcome to this week's lecture on Web APIs, async await, and HTTP status codes. So this lecture is going to cover some topics that go hand in hand with real-world C# development. Things like Web APIs, asynchronous programming, HTTP status codes. How do we talk to things on the internet is really what this is all about. And this is why these three things belong together. Almost every time your C# application talks to the outside world, a weather service, a payment processor, a database hosted somewhere else, you're most likely talking to some kind of web-based API. And because that call travels over a network, it takes time, which means we need to learn how to use these async and await keywords to avoid freezing our application while we wait for that response. And once that response comes back, you need to know how to interpret its status code to find out whether it actually succeeded. So by the end of this lecture, you'll be able to call a real API from C#, do it asynchronously without blocking your program, and correctly interpret whether that call succeeded or failed. So let's start with some fundamentals. What is an API? API stands for Application Programming Interface, and it's essentially a set of rules that lets two different pieces of software talk to each other. It defines exactly how one application can ask another for data or services and exactly what shape the response will take. So have a look at this diagram. Your C# application sends a request through the API. That request reaches some remote service or database, and a response travels back the same way. The API is the agreed upon contract in the middle that makes this whole exchange possible. Your app doesn't need to know anything about how the remote service is built internally, it just needs to know the API's rules. So why does it matter? Well, there are really four reasons APIs are everywhere in modern development. We have reusability, which it sounds like I keep harping on, but the idea that we can reuse things we've already built just makes us, lazy, which makes us more efficient. We want to be able to use functionality someone else has already built or things we've already built instead of recreating it. Scalability, that's where APIs let us interact with massive systems and databases without needing to manage a lot of that infrastructure directly. Modularity is where our application can be built as separate independent pieces that talk to different APIs and makes the whole system easier to maintain. And then the idea of interoperability. APIs let completely different platforms and technologies communicate, even if one is written in C#, the other in Python, and the other in Java. So the takeaway here is that APIs let us stand on the shoulders, essentially, of existing software instead of rebuilding everything from scratch. So let's take a concrete look at actual C# code that calls an API. And there are 3 steps every API call is going to follow, and you'll see this pattern again and again, so it makes sense that it will start to become very familiar. So step 1, we create an HTTP client object. This is the .NET class specifically built for sending HTTP requests. Notice the using keyword in front of it here in our example. That ensures that the HTTP client is properly disposed of when we're done with it and we don't have to remember to close it. Next, we call our client objects getAsync, and that can pass in the URL of the API endpoint we want to reach. Since this is an HTTP request, we are literally calling out to a URL that hosts the API, and we are going to await that call. Notice that await keyword. This sends an HTTP GET request and gives us back an HTTP response message. And we can see that we can catch that message, and then we call ensure success status code, which is going to evaluate whether or not that response was successful. and it's going to throw an exception automatically if something went wrong. So it reads the response body as a string and puts that into our string content by calling the read as string async. So the final step, and this is the step a lot of new developers find a little magical the first time, we take that string of usually JSON text and we deserialize it directly into a C# object using the JSON serializer.deserialize method. And when we specify the type we expect, so example data, there is the type, so that would be a class that we have defined. When that line runs, data.id and data.name are usable and strongly typed C# properties, even though a second ago, before we deserialized, they were just text. So this same three-step pattern, send the request, read the body, deserialize the response, is how the overwhelming majority of API calls work, whether they're C# or any other language. So once you're comfortable with this pattern, you can call almost any API that you'll encounter and know how to handle it. So let's dig more into asynchronous programming and talk about why we used the word await in that code example and what would happen if we didn't. So network calls take time. And that might not seem like a lot of time to us because sometimes we're talking about milliseconds, but sometimes we're talking about seconds. And if your code just sits and waits for that response the naive way, your entire application freezes during that wait. Because essentially, and I've used this term thread before, all of your application is working on one kind of stream of consciousness that we call a thread. And it is accessing memory and it gets placed in the CPU, but that thread can only do one thing. So while your application is waiting for a response, that thread locks up and the entire application freezes. So in a desktop or a mobile app, that means the UI becomes unresponsive, the user can't click any buttons, your app might hang, the phone operating system might be like, hey, this application has probably crashed. Do you want to close it? But that's not really what's happening. In a server application, things get even worse because that thread cannot serve any other users while it's stuck waiting. So we can look at a comparison here. On the left, in our synchronous or blocking code, the request goes out and then the UI just stops. Step 2, 3, and 4 are literally just various flavors of waiting. We're highlighting in red, nothing else can happen. Only once the response finally arrives does the UI respond again. But what we want is the example on the right, asynchronous non-blocking code using await. The request goes out, but this time the UI stays responsive immediately. Essentially, a second thread is opened. The user can keep interacting with other parts of the application, and that background work can continue on that original thread. Then when the response eventually arrives, the result is simply used at that point without ever having frozen anything in the meantime. And this is the entire value proposition of async and await. You get the responsiveness of non-blocking while still writing code that reads top to bottom, almost like it was synchronous. And that's not the way that it used to work. Older programming languages, you could handle and create asynchronous type requests, but it did require a lot more heavy lifting. So those of us who are now fortunate enough to be living in a time where the async and await keywords are doing that work for us, we can just simply be grateful and learn how they work. So let's get a little more precise about what these keywords actually do, because they always work as a pair, and that's why we are talking about them like they go together. Async is a modifier that you put on a method to indicate that it contains asynchronous operations. An async method has to return either a type of task for a method that doesn't hand back a value, or task of some type T, which is where we define some type of value. So it's going to return an object or a string or something like that. Marking a method async is what unlocks our ability to use await inside of it. So then the await keyword is what we put in front of the asynchronous call. It pauses execution of the current method at that exact point until the awaited task finishes. But critically, it does this without blocking the thread. The thread is freed up to go do other useful work while it waits, and your code picks right back up where it left off once that result is ready. So take a look here at our example, the perform tasks async. It's marked async and returns task. Inside, we await the task.delay, which has 1 second passed in as an argument. We print a message and then await task delay for 2 more seconds and print another message. Each await pauses just that method. Nothing in the rest of the application is frozen during those delays. Down in main, notice that main itself is also marked async and returns a task and awaits the perform tasks async. This is an important pattern because async tends to be contagious up the call chain. If a method awaits something, it usually needs to be async itself, and whatever calls it often needs to be async too. So keep this in mind if you are writing an application and you're getting where the application hangs in places you didn't expect. It may be that you didn't take your async up the chain far enough. So some common pitfalls. Async and await are powerful, but there are some mistakes that are extremely common amongst people learning this for the first time, and some of them can cause some serious problems in our application, so we want to understand how to handle them. So first, avoid using result and wait. These are ways of synchronously blocking on a task instead of awaiting it. And so this is a tempting shortcut. Like, I don't want to make my method async. I don't want to have to call await. So I'll just call .result on the task to get the value directly. Don't do this. In certain contexts, especially when we get into UI-based applications, this can actually cause what we call a deadlock, where your program freezes permanently. The operating system doesn't know how to resume, doesn't know how to get it out of that locked state. It also throws away every benefit of going async in the first place. Second, we always await our async calls. If you call an async method but forget the await keyword, your code doesn't wait for that operation to finish. It just moves on immediately to the next line. Now, this isn't a compiler error, but the compiler will throw a warning for you to let you know that you've accidentally done this. This is a sneaky source for bugs because the code often still compiles fine. It just behaves unpredictably because you thought, hey, it's going to wait because you used async, but you forgot to use the await keyword where you needed. Our third one is propagating async all the way up. So if a method awaits something, and that method call, it should also generally be async and await that call, and so on up the chain. Trying to stop the async chain partway up, usually by reaching for something like .result or .wait, is exactly the same mistake as point one. You will end up either with unexpected results, with sometimes locking up or deadlocks, or your application crashing, or your users just get really frustrated because your UI hangs in ways that they didn't expect would happen. So let's shift gears slightly because we've talked about sending requests and getting responses back, but how do we actually know whether a request succeeded or failed? And the answer is HTTP status codes. These are a 3-digit number that comes back with every single HTTP response. And if you are building an API, which you'll get experience doing if you take the advanced C# class, or if you just want to dig into making APIs, you have to be able to return this HTTP response code so that the receiver on the client side or whoever is consuming your API knows what's going on. So you don't need to memorize these codes. They're pretty easy to look up. The first digit alone, though, can tell you which of the 5 broad classes the response falls into. So codes under the 1 are informational. This means your request was received, the server is still working on it. You really rarely deal with these in actual application code. 2s are successful, so things like request was received, understood, accepted. So 2s are generally the class that we're hoping for every time because that's a green thumbs up. 3s are for redirection. So this means further action is needed to complete the request. The resource has moved somewhere else. You have a bad URL. They've changed it to something different and you need to update your records. People who work on API responses or who have like servers set up to answer responses from applications can set up a 3x redirection so that people who are calling in with their different client applications know that there is an update needed. 4x's are client errors. So something about the request itself was bad, maybe syntax was wrong, maybe you don't have permission. So this keyword here is client error. That means your request had the problem. So maybe you called an API method, but it, requires a parameter you didn't send, or you don't have permission, your key is bad, something like that. 5x's are server errors. So that means the server received a perfectly valid request, so not a client error, but failed to fulfill it for some reason. So that means the problem is on the server side and not on your side, unless you also maintain the server. So mental shortcut. 2s are good news. 4 means you probably need to fix something about your request. 5 means the problem is probably out of your hands. And the rest of these you most likely won't mess with unless you get into really deep server programming. So let's talk about some specific ones that you'll run into pretty consistently as a developer. So 200, that just means okay. That's the common status code that your browser gives to your, or that your websites give to your browser. So far and away, the most common success code. This means the request worked, the server returns the data you're asking for, everything is good. 201 created is also a success, but it is specifically used when your request caused a new resource to be created. Maybe you added a new record to the database, post request that needed to make an update or something like that. You would send back a 201. 204 no content is a success, but it also implies that there's no message or data to send back. You see this pretty constantly on things like delete request, where succeeding doesn't require returning any data. You just want to let the client know that it happened. 400 is a bad request. Your request was malformed or invalid in some way. Maybe a required field is missing or the JSON's not formatted correctly. 401 is unauthorized. So some APIs need authentication, you need to pass credentials or a key, and you either didn't provide these or you provided invalid ones. 403 is forbidden, and this is subtly different from 401. Here the server knows who you are, but you don't have permission to do the thing that you're trying to do. So maybe you have a key that lets you read information from the API and you sent a delete request. You don't have permission, so you're going to get a 403 response. 404 is not found. Probably the most famous HTTP status code of all. That means the resource you've requested simply doesn't exist at that URL, and that's the response you got back. 500 internal server error. This means that your request was fine, there's no problems with it, but something broke on the server side while trying to process it. This isn't like something usually that you can handle. It's squarely the server's problem, not yours. But again, if you are the API maintainer and you have written the server code, then you'll need to go dig into why the request was not handled. So knowing status code categories is great, but how do we actually check them? So let's take a look at a practical pattern. We create our HTTP client we call our get async just like before, awaiting the result to get our HTTP response message. So the key line here is if response dot is success status code. This is a convenient built-in property that's true for any status code in the 2XX range. If you don't have or want to manually check 200, 201, then is status success code is going to handle that range check for you and just return that Boolean response. So if it's successful, we read the content as a string, just like in our earlier example, but look at the else branch. This is what a lot of beginner coders skip. If the request was not successful, we want to cast our response.status code to an int so we can actually get the numeric code returned and print a clear failure message that includes the code, which can be very helpful for when we are needing to debug. So why does this matter, right? We have three things happening here. Get async sends the request and hands back that HTTP response message object. Is success status code gives you a fast and built-in way to check for any of those 2x codes without writing your own range comparison. If something fails, casting status code to an int gives you the actual numeric code, which you can log, display, or use to decide how to respond programmatically. So this is the pattern to use and remember. We never assume success, we always check. So let's pull everything together, our APIs, async usage, status code, into some best practices that will serve you well anytime you're working with web APIs in C#. So first, remember we never block on async code. We kind of covered this already, but it's worth repeating because it's important. We want to avoid using .result and .wait and use await consistently all the way up our call chain. Always check status codes. Don't assume an API call succeeded just because there's no exception thrown. We check is success status code explicitly or use ensure success status code and handle the exception it throws on failure. Either approach is going to work, but silently assuming success is how bugs slip into production. We plan for authentication and errors. The examples that I've shown you are really simplified. Real-world APIs frequently require authentication tokens or API keys that are sent in the request header, and they can fall in all sorts of places. We also can see APIs fail in a lot of different ways than what we've shown. I also did not include things like try-catch blocks in this code just to keep it simplified for slides. So we want to plan for things like timeouts, rate limiting, malformed responses, and build our error handling with that reality in mind. Finally, we reuse our HTTP client instances. So kind of a subtle detail, creating a brand new client for every single request can actually exhaust system resources like network sockets over time. And the recommended pattern is to create one HTTP client and reuse it across many requests rather than constructing a new one every time we need to make a call. So key takeaways. Let's bring it all together. APIs let applications communicate with each other, letting you reuse existing functionality and data instead of rebuilding it from scratch. In C#, HTTP client sends the request and JSON responses are deserialized into strongly typed C# objects using JSON serializer. Async marks a method as asynchronous, and await pauses that method until a task completes without blocking the thread, which keeps our application responsive. Never block async code with things like .result or .await. Doing so can cause deadlocks and defeats the entire purpose of going async. Every HTTP response carries a 3-digit status code that falls into one of 5 classes, and the first digit alone can tell you the general category. Always check, is success status code in your code? Never assume an API call succeeded just because your code didn't throw an exception. So looking ahead, we'll start to build on this foundation by looking at how to send data to an API, make the post requests, handle, the response, deserialize our JSON, and your assignment is posted so that you can get some practice working with a public API and writing a C# application that calls it asynchronously, checking our status codes, getting information. And so we'll be well prepared for further work with APIs after the end of this lesson. So remember, reach out if you have questions, if you need help, if you have anything to talk about regarding the lectures, or you just need help with your code. I am here to help. So I'll see you in the next one.